In the last class, we were doing convex learning problems. So, a convex learning problem, a learning problem H, the hypothesis class, and Z, the samples, and then the loss function was called convex if the hypothesis class H is a convex set, and for all the samples, for all Z in Z, the samples, the labeled samples, the loss function L Z is a convex function where the loss function L is denoted by F from H to R, and where F was defined as L W Z. So in a convex learning problem, our hypothesis class has to be convex set, and the loss function is a convex function, and how the loss function is related to the F is shown here. So what we have proved in the last class is that, and we have shown an example of a convex learning problem, and that was the linear regression with squared loss. So we have seen this in the linear predictor chapter, and in the last class also we have shown that this is a convex learning problem because the hypothesis class is basically the set of all normals to the plane, and hence the set of all those vectors W hypothesis class was characterized by the set of planes which are characterized by the normals. So this set is indeed, set of all W is indeed a convex set, and then the loss function in the squared loss function with the loss defined as Wx minus y for the linear regression problem is a linear function, so it's convex, and even the square of that is convex. So overall, this we proved in the last class that it's a convex learning problem. And what we have seen is that convex learning problem by themselves are not necessarily pack learnable, and we have proved this in the last class that so the learnability, non-learnability of linear regression. So we have seen this in the last class, the non-learnability of linear regression. So this essentially tells us that linear regression, which is a convex learning problem, is by itself not a learnable. It's not pack learnable. Okay. So not everything is good if we have a convex learning problem. For machine learning, we need a lot more. Okay. The fact that it's convex, it does mean that I can minimize the loss and so on, but for machine learning, we need a lot more than convex setting. So then a natural or maybe let us say some ideas that we may want to play around is what if the what if the thing that created problem in non-learnability was maybe the unboundedness of the hypothesis class. So we can say that, okay, let us bound this, okay, and see whether that leads to learnability. So we can kind of say that we would like to bound it. Okay, so a possible solution for this is to add another constraint, on hypothesis class H. So this constraint could be that we bound it. Okay, so let us say we bound H, the hypothesis class. So for the linear regressor case, so or linear regressor, or let us say any parameterized function. So okay, so in this case, so let us say the weights of our predictor are bounded. So assume that, so by boundedness we mean that for every, so this is true for the linear regression, that the functions are characterized by W, and we further demand that W is less than or equal to some B, a constant. So B here is a constant. So basically we mean that we bound this normal vector by a constant B. So a natural question here is, is this going to be enough to make it pack learnable? So this additional constraint that we put on the hypothesis class, at least for the linear regressor, the hypothesis class is W, set of W, and if we bound those, will it solve the problem? It turns out that this also won't suffice, and this is given by example 12.9, which is similar to example 12.8 we proved last time. So example 12.9, so as in example 12.8, consider a regression problem. So the same problem we saw that it is still not learnable even with this boundedness. So okay, so regression problem with squared loss. So however, this time we let H to be set of W such that W is less than or equal to 1, be a bounded hypothesis class. So be a bounded hypothesis class. So even with this bound, this H is convex. So clearly H is a convex set. Okay, so clearly H is a convex set, and so similar to what we have done in example 12.9, you can prove this as an exercise, that this is also not learnable. The arguments are very similar, so I will leave this as an exercise. So exercise so that it is not learnable. Okay, so even with this boundedness constraint, it's not learnable. So clearly we need a little bit more than this. Okay, so what else we can have apart from this? So then we move to some other class. Obviously, we are trying to build on this. So we are saying that convex is a good thing, at least the loss is convex and so on, and optimization will be very optimal. So, but boundedness also didn't work. But then it's like we will keep adding some ingredient. So boundedness as just one additional thing doesn't help here, but we need something on top of this. So so what we will do is something like we will also add Lipschitz continuity, and then with these three arguments, convex, Lipschitz, and bounded, this becomes learnable. Okay, so we will need additional argument here. Okay, so we need an additional argument here. So hence we will define a new class which is Convex-Lipschitz. So let us say we also make a space for this. So we have convex Lipschitz bounded learning problems. So convex we know, bounded we know. Basically, Lipschitz is something that's additional. So a learning problem H Z L is called convex, SCHITZ, and bounded with parameters rho B if the following holds. If the following holds, so in this case, so certainly we are going to require the boundedness, and we will also require the Lipschitz continuity of the loss function. So in this case, the hypothesis class H is convex, and for all W in H, we have norm of W is less than equal to B. And then we also need the Lipschitz continuity as an additional argument. So for all Z from the sample set Z, the loss function L is convex, and rho Lipschitz function. Okay, so these are the requirements we have for convex Lipschitz bounded functions with parameters rho and B. And with this setup, as I said, the learnability will be ensured. Okay, so we can look into some examples. So let us say example 12.10. So let X be set of all X in Rd, and norm of X less than equal to rho, and Y the set of labels be R, and let H be set of all W in Rd such that norm of W is less than equal to B, and let the loss function function be L W X Y is Wx minus y. And so indeed this corresponds to the regression problem, but the difference here is that we take absolute value of the loss. Okay, so this corresponds to with absolute value loss. So that's the absolute value loss we have. And Lipschitz continuity has not been enforced yet. No, okay, I mean, it will be enforced in some other way, in the sense that these samples are now taken to be bounded by rho, and this should imply, so in here what we need is this loss function is convex and rho ellipsis. Okay, so this has not been directly stated there that L is rho ellipsis, but the additional thing that we see here is that these are bounded. So this we believe will imply that L will be a rho ellipsis as a consequence of that. Okay, so so that perhaps we have to settle it, but so we can make a statement that we restrict the hypothesis to be and so everything has been stated. W is bounded, and L is convex. It's the absolute value function as a function of W, and that's it. So now we can claim that, so this is a convex. So we can use a shorthand notation so that we don't have to write CLB, let us say, Convex-Lip-Bounded. Okay, so this is a CLB. Okay, so to compare it with this definition, then what we see is that we are not given directly that L as a function of W. Okay, Z is fixed. So it's like for all Z fixed as a function of the weights W is convex and rho ellipsis. Okay, so it is not given to us directly, but as a simple analysis we can actually prove that it's L will be, small l will be ellipsis in W. Okay, so then with we can memorize this basically and then proceed to prove that. So the thing that is left is to show is that L as a function of W, so L this, and for any Z is convex and rho ellipsis. Okay, so basically to prove this is a rho ellipsis, let us pick two weights, let us say U and V. Okay, so consider UV, and these are in RD, right, from the hypothesis class basically. And then we have to say that the LU minus LV is, we have to prove that it's less than or equal to rho U minus V. L goes from Rn to R, and it's defined as a mod and so on, but W's, compared to the previous example, W's are d-dimensional. Okay, so we will prove that it's L ellipsis, I mean rho ellipsis. So L mod of this, because it's real valued, and U comma Z, and Z is the XY sample. So combined pair is written as a Z minus L VZ. Now L U Z by definition, okay, we may have to split this anyway, right? But let us say Z is XY. So the feature and the label. So in this case, then I will use that. So this is U X minus Y, and this is the mod, right? And then there is outside mod also, okay? And minus V X minus Y, okay? So, and we are supposed to prove that whole thing is, so we have this in our mind, that whole thing is less than rho mod U minus V, or in fact the norm of U minus V. Okay, so this is what we are thinking, and we have to use some manipulate this a little bit. So recall some results like, how will you prove mod X is ellipsis, right? So basically the result that we may need is less than or equal to mod X minus Y. Okay, so this is the result that we recall this inequality, and we will apply it here. So this is our whole thing is X, this whole thing is Y. So, and so this becomes less than or equal to, and mod of Ux minus Y and minus Vx plus Y. So Y gets cancelled, and we have U minus Vx equals to mod of U minus Vx, and then the natural thing to do is Cauchy-Schwarz to split out U and V, and X is given to be less than or equal to rho. So that's, then you immediately have this this result, right? So this is less than or equal to norm of U minus V norm of X. So all are norms, so mod can be removed. So this is equal to norm of U minus V norm of X, and then it's given that norm X is less than or equal to rho. So now it becomes less than or equal to rho norm of U minus V. Okay, so this implies that L is rho ellipsis. So and another class is convex, smooth, and bounded. So now instead of ellipsis we are saying smooth. So that's another class that is also learnable. Okay. So recall from the last class, convex learning problem are not learnable. Then we bounded it. Today in the beginning of the class, we said that what if we bound the hypothesis class, but that also didn't work. And then we said that we need something more, and then we added ellipsis continuity, and then we will show that this class is learnable. So the another definition that we have is 12.13, and this is convex, smooth, bounded learning problems. Convex, smooth, bounded. Okay, and so basically learning problems. So we can define this class. So as usual, we take the hypothesis class H, the set of samples Z, and the loss function L, and this defines our learning problem. So this is let us say we call this CSB, okay, in short, and the previous one was CLB. Okay, so this is convex, smooth, bounded learning problem. So we can also make LP also a learning problem, because the whole thing we have to say, right? So is CSB LP. Okay. So it is defined to be a convex-smooth-bounded learning problem with parameters beta. So beta, as you can see, it corresponds to the smoothness here. If following holds. So as usual, the boundedness of the hypothesis class is needed. So the hypothesis class H is a convex set. And for all W in the hypothesis class, the W is bounded by a constant B. And the loss function is convex, and beta is smooth. Okay, so in this case, so for all Z from the labeled sample Z, the loss function L Z is convex, non-negative, and beta is smooth. Okay. So this is the definition of CSBLP. Loss functions usually are non-negative. Just to be sure, we put it there, and we have the beta smoothness as well. So for this, we can have an example where we will show that this is an example of CSBLP. So let us look into this example. So in this case, we have our X to be set of all X in Rd, and such that norm of X is less than or equal to beta by 2, and Y to be set of all real Y coming from a set of real numbers, and then H, the hypothesis class, is set of all W in Rd, such that norm of W is bounded, and the loss function L W x y is W x minus y whole squared. So this is again a regression problem, but now we change to squared loss, and this is this belongs to the category there. Okay, so basically we have the smoothness guaranteed. Loss is non-negative for sure. Okay, and the beta smoothness condition holds. So basically you have to show that because everything else is already there. So H is a convex set. So this set of all W such that norm of W is less than or equal to B, you can show that this is a convex set, and yeah, with norm of W less than or equal to B, so everything is here. And loss function, this is a convex function, right? You can in this case it's differentiable, so you can take double derivative also, and the Hessian will be non-negative. So you can do a second order convexity check here. So this is convex, and then it's non-negative. So the only thing you have to show is that it's beta smooth. To show L is beta smooth. So I leave this as an exercise because I did the first example. So this is again should be again a couple of lines. Okay. So what we have described is that we have described two classes, convex-ellipsis-bounded and then convex-smooth-bounded, and these two classes are learnable in the pack learning sense. Okay. And okay, so if we look into these classes, then what we have here, at least let us say focus on, okay, this is convex, let's say, okay, and even bounded and so on, and but let us see this case where we expect the loss to be convex. Now, as we know, sometimes loss functions may not be convex. Okay, for instance, if I take a 0, 1 loss, okay, so 0, 1 loss is not a convex function. Okay, so basically any kind of a thresholding in general is not convex. So this is not a convex function, right? So in the 0, 1 loss, we said that if W transpose X is let us say less than 0 or greater than 0, it doesn't matter. Okay, so it depends on which class I am identifying. So then we say that predict 0, and then this class W transpose X greater than 0, then we predicted that it's 1. So this function is indeed like this, and then like this. So certainly this is not a convex function, right? So there are practical loss functions where the convexity is violated, and we know that 0, 1 loss is a valid loss function used in machine learning. So what will you do in those cases, right? So is there a way to still make these problems learnable with those kind of loss functions which are not necessarily let's say convex? Okay, and so a natural argument that can go with this is as a natural, because we need the convexity as such, right? So because without convexity you may not necessarily guarantee the optimization. Okay, because solving an optimization problem needs optimally I have to find a minimum of a function, then I need that function is convex. Okay, then the optimizer is guaranteed to be guaranteed to find the minimum. But in general it may not, because it may get stuck in local minima, and hence you can never say make the whole loss less than epsilon. Okay, so it is quite clear that convexity is needed. So what do you do, right? So you have problems where loss functions are not convex, but then you have but then we do have cases where from the learnability point of view we need convexity. So what do I do, right? So in this case a natural thing to do is, can I have an approximation of these losses via some convex some convex function, right? So basically we are looking for something surrogate. Okay, so can I have some surrogate of these losses which are not convex, and I optimize using a loss which is convex, but it somehow approximates this as well. Okay, so that's what we are going to do, is to look for ways where loss functions may not be convex. So trying to generalize these ideas, but we use a surrogate which is a loss which is a convex. Okay, and then many problems where loss is not convex becomes a convex learning problem. Okay, so or even pack learnable. Okay, so this is the thing that we will do as a next step, introduce surrogate loss functions. The section 12.3 is surrogate loss functions. So what I have said I will just write down. So consider the problem of coming from the linear predictor that we did in some time ago, and in the linear predictor problem, we recall 0, 1 loss, and that was W x y, and this is 1 and y not equal to sign of Wx, and close this, and this is 1 y Wx. So this was equivalent to this, right? So in the linear predictor, we said that our losses were defined in a way that when W transpose X y is less than equal to 0, we were predicting to be 1 class, and then so basically, I mean, if the classifier is doing well, because this holds in both the cases, right? Because if W transpose X is less than 0, okay, and this is the positive class, then it makes it less than 0, and if it's the negative class and this sign is positive, then still it's less than 0. So if I hope you can recall this, what we did in the previous classes. So what this essentially says is that if your classification is good, then we say that it's 1, otherwise it's yeah. So this is how the loss is defined as a 0, 1 loss, right? And now we want a surrogate of this. So if I have to draw this as a, because the surrogate is easier to see when we, so on the x-axis we have y Wx. So if y Wx is greater than 0, yeah. So if it's greater than 0, then it will be 0, and otherwise it's 1, right? So L01 loss is like this. Let us say this is our 0, this is our 1, and then this is our loss. Yeah, let me do it like this, and then okay. So if we look into the 0, 1 loss, then it's like this. If y times W x is, did I draw it correctly? Yeah. So this was, yeah, right. So this was supposed to be 0, right? So if it's greater than equal to 0, then so maybe I should have drawn it from here, right? So if it is greater than equal to 0, then so y times W transpose X, if it's greater than equal to 0, then it's 0, otherwise it takes 1. So this is the 0, 1 loss that we define. So it is clearly not convex. And so, but we want to make it learnable, right? So to make it learnable, we will define some surrogate loss, okay, which will be convex. Okay, so let us define a surrogate loss, which I will pass it through here, and then surrogate loss in the bold. Okay, and this is what we will approximate by. Okay, so we have this 0, 1 loss, but we will try to work with this. Okay, so obviously we have to interpret what is the meaning of the loss, right, with respect to this. Okay, so basically from here, what we learned with this surrogate loss is that if it's less than 1, right, so y transpose X is less than 1, then this is like something positive, right, or or if it's less than 0, then it's like it's greater than 1. Okay. So this is how we have to kind of make a correspondence here, that when the original loss was less than 0, how do we interpret it with this new loss? Okay. So we will build on this. So let us now define this new loss in a more in a rigorous way, what exactly it means in reference to the 0, 1 loss. So that's the idea. This is not convex, but we use a surrogate loss function, and in this case we call it a or let me first define it, and then I will call it whatever name it is. So we define a surrogate loss function which is convex. So in this case this is convex, obviously, which is convex. Yeah. And it upper bounds the this loss, right? And it upper bounds So this is actually part of the definition of a surrogate loss function, that usually surrogate loss functions are defined to be convex, and it upper bounds the previous loss, okay, for which it is a surrogate. So in general, we define surrogate loss separately. So it should be convex, okay, just that we identify that this is the generic way to define, okay, should be convex, and it should upper bound, okay. The original loss, okay. So so this is a generic definition of surrogate loss. So that's why we separated this out, and so in this case that we have identified one possible surrogate loss, can we kind of like write this down formally, okay. So for the 0, 1 loss, define the following surrogate loss. So this is L hinge of W x y, and this is defined to be maximum of 0, 1 minus y w x. Okay, so the graph that I made here is defined exactly like that. So what it says is it's a maximum of 0 and 1 minus y times wx. So if you see from here, then it's 0 when it's negative, basically. So I mean, I'm looking at the y wx. So let's see. So y wx, if it's greater than 1, if it's greater than 1, then it's negative, and negative of 0 and maximum of 0 and negative will be 0, right? So that makes sense that from here onwards is 0, right? And then if y transpose x, y of w transpose x is less than 1, then it is greater than equal to 0. Okay, so in that case, the maximum of 0 and greater than equal to 0 will be the greater than equal to 0, which is given by this guy. Okay, which is the line y1 minus y w comma x. So if you plot that, that will be the line. So this is the hinge loss. It's a very popular loss. You will see this in machine learning from time to time. So for the moment we write this. We kind of so we just like write down this case that we have discussed. So for y wx greater than 1, greater than, yeah, if it's also equal to 1, it's fine. Okay, so it's greater than or equal to 1, then the maximum of this will be 0. Okay, then L hinge of w y is 0, and the second case is for y wx less than 1, L hinge w xy is equal to 1 minus y wx, okay, which is this line that we are talking about. Okay, so that's it. So that's about the L hinge loss, and this loss is convex, and that with this choice of loss for the 0 1. So even if I am doing classification problem where I am supposed to use 0 1 loss, I will make it a convex convex bounded and yeah, CSB, right? So convex smooth or bounded, or convex ellipsis bounded, CLB. Okay, so either cases it doesn't matter. So the main problem for us was that the loss could be non-convex. In both the cases we needed it convex, and we can make it convex with surrogate loss function, and hence we make it a learnable problem. So this is what we have, and so once we have this change in the loss, then obviously one may ask what error or additional error I'm going to introduce with this choice of surrogate loss functions, right? So we can kind of characterize this losses, the training loss, and so on. So in general, what we expect is that if I indeed start with this loss, which is the hinge loss, then I have the similar expectation that the training done on this, which is like LDS, the loss for the training after training, the loss that I make and the actual loss that I have, both are bounded by epsilon. Okay, so this is something we have. So the generalization would mean the following. It would require the following. So generalization requires. So by now we have seen this a couple of times. So the generalization with this would require that this is minimum of L hinge So this is what generalization means, that I come up with an algorithm which trains on a given sample, and then I check the total error made on also the new data or whatever which it has not seen. So this error that I have, it is not far from the actual error. Okay, the ideal hypothesis that you will have, okay, compared to what you see in the training. Okay, so they should be kind of close, meaning they should be bounded by epsilon. Okay, so this is what generalization means. So training error is not far from the ideal error, and we want that after we have introduced the hinge loss, we want that the hinge loss also generalizes in general. Okay, so for the test data and so on. This is the expectation, right? So, and where L hinge W for the D is expectation of x y from D, and L hinge W x y, where the loss is defined in that way. So it's like the is the way it's defined, that what is the error in general it does on all the samples taken from the actual distribution. So now what we know is that this is a surrogate of the 0 1 loss. So by definition the surrogate upper bounds the kind of or we can lower bound the L hinge by the L 0 1 here. Okay, so L 0 1 since L 0 1 is kind of the ideal loss, I mean you can think of, so it will make a lesser error than L hinge. Okay, so L 0 1 will be lesser than this, hence it will be lesser than this, because this is a surrogate. So we expect that the surrogate learns a little bit less optimally compared to the actual loss. So that actual loss will be lesser loss, and this guy, and this is something is needed, right? So this is something is required. I'm not saying that this is a statement, right? This is something like we may have to prove it, right? So that this is, if I have a surrogate loss L hinge, then it should generalize and then it should satisfy this inequality. Okay, this is a requirement. But what we know is that the original loss function must have been making a lesser loss compared to this. Okay, because that was kind of the ideal loss for that problem. So with that in view, we can write that so we have L 0 1 loss over the distribution D A S, and this is, so just for completeness I will write this line as well. So L hinge is less than equal to L hinge and AS, and then this is less than equal to minimum of W in H, and then LD hinge W plus epsilon. Okay, so this is something we have. So we are basically trying to interpret, right? Now I have introduced a surrogate loss, then what are the consequences of the generalization, right? So we are kind of trying to see how to characterize these things, right? So so I have this original loss, surrogate loss. So what kind of errors they will incur in while doing this, right? So we will write one line after this, and that will kind of help us understand what will happen in general. Okay, when we work with surrogate loss, what kind of approximations, optimization, error, how they are related. So so what we will do is that we will do some add and subtract. Okay, basically I will subtract by L 0 1 so that it gives me a way to kind of compare hinge and the L 0 1. So we will subtract basically L 0 1 in here. Okay, add and subtract on the right hand side. Okay, so on the right hand side, on the right term, and we add and subtract we will add and subtract the term which is minimum of minimum over W in H and L01 D and W. So the left hand side remains the same. So this is LD01 and AS, and this is less than equal to minimum of W in H and then LD. So I believe I will do the first add here itself. So 01 dW plus minimum of W in H, L hinge dW, and then minus of minimum of W in H, L01 dW. Okay. So as you can see, I have added and subtracted minimum L01 dW, and they have subtracted. So they cancel out and they give me the same thing. But it's a way to interpret. Okay. It's a way to interpret the training error that I have made with the original 0-1 loss, and how it is related to when I start working with the surrogate loss. Okay. So this is a generalization error, okay, that we know. So this is okay. This is the generalizability, how far I'm the test error and train and train error. Okay. So that's we know, and this is something. This is the error that that I will have with the 0-1 loss. Okay, and this is the test error I will have on the 0-1 loss. So after I have, let us say, I have trained on some samples, and then I will check the actual error with the 0-1 loss. So that's this, and then this tells us that how far are the losses with respect to the hinge loss and the 0-1 loss. Okay. So if my if the error I make with the hinge loss and the one I make with the 0-1 loss, they are very big, then the upper bound will be very bad. Okay. So ideally the hinge loss, the error made by the hinge loss and the 0-1 loss, if they are minimized, okay, and this was your original loss itself was a good loss, in the sense that it can fit the test data well, because there is a test data here, right? There is no sample here. So if it did well, if it itself was generalizing very well, then this loss will be very small. Okay, and our hinge loss and the original, the 0-1 loss, if they are their errors are very close, okay, then also overall the training error here for the 0-1 loss will be bounded by all these terms. So I'm going to write down these things for the actual name of these things. So so the first term will be our approximation error. Okay, so this we call it approximation error. Okay, so approximation error. So this is the term mean of W in H, L01 dW. So this is the approximation error with our original loss, and so this is our approximation error. And then we have estimation error. So this is how we estimate it with the surrogate loss. So this is estimation error. Let us say is first. Let us this is optimization error. So we call this optimization error, this second term here. is an optimization error because we saw that optimizing with a non-convex function is difficult because it may lead to some local minima. It may get stuck in local minima. So hence we built a surrogate loss, and then we thought of optimizing with the surrogate loss. So hence we call this an optimization loss. We could not do an optimization for this, but then we kind of use some other objective function. So here we may incur some error, okay, while optimizing. In other words, the minima of the L hinge may be found at a different place than minima of the 0, 1, okay, because that can happen, because if it's a non-convex function and I am approximating this, so if I'm lucky, then I'm approximating this by a surrogate, okay, then my surrogate is indeed a convex function, and it's and the minima I'm working with the surrogate, and minima of that I found it here. And in this case, I'm lucky that the minima of the surrogate is same as the minima of this. Okay, so this is the ideal case where the minima of the surrogate is same as the minima of the original loss. But it may not be the case, right? Because if I may have obviously a convex function, I mean non-convex like that, but then the surrogate that I'm building is like this, okay, and then I may have matched the minima maybe here, which I didn't want to. So I want the minima of the surrogate to be somewhere else. So this is my surrogate. This is our original, and minima of this guy I believe is somewhere here, let us say, and then minima of this guy surrogate is somewhere here. Although I have not done the good job here as well, I don't know why it looks same again. First thing is to draw the convex surrogate first. This is my surrogate, and oh, it cannot go like this again, I'm sorry. So yeah, I will make it minima here, let us say. So first fix the target, that x star somewhere here I have to come, make it a minima. So it's non-convex because it's wobbly, right? It's not convex for sure. Sorry that it took more time than I thought. So this is our minima for the original loss, and the minima for the surrogate loss, they vary. So hence this is the optimization error we are talking about, right? And this may lead to this quantity being large, okay? So that's why we call this an optimization error, okay? And last one is obviously the generalization error. You can say the epsilon that we have is the same epsilon that we came from the generalization part, right? So, but the name given is like estimation error. So basically, estimation error is the error caused by the fact that we only receive the training data, and based on the training data, we see how much it generalizes. So basically, that's the same epsilon. I got some loss on the training data, and then I see how bad I did compared to the actual loss. So that's the estimation error, or I can also say generalization error, okay, with respect to the hinge. So these are the three things when we introduce a surrogate loss functions. Then so as I keep saying, machine learning problem is much bigger than just an optimization problem, right? So machine learning problem, many things come in picture. The hypothesis class, generalizability, obviously. So So we found a class which is convex, ellipsis and bounded. So we have the two classes we started with today, convex, ellipsis and bounded, and convex, smooth and bounded. And I have claimed in the beginning that these two classes are learnable. And given other things, the boundedness and the convexity of the hypothesis class, one of the things that may not be satisfied in general is the convexity of the loss function. Okay, and this is an example where surrogate functions can be used with some optimization error. And with this surrogate loss function, so our problem changes a little bit. Okay, so given the problem with this loss, now we will say that our loss function is now this. So we change the problem a little bit, but then we made it learnable problem. Okay, back learnable. So obviously, when we change the problem, we have to be careful that the change done was a good one, bad one. So this is how we are characterizing these things. So, one of the things we ask is, okay, in this case I added a hinge, right? But for given class of problems, what are the ways I make the problem learnable, right? So in this case I found one convex surrogate. Okay, that's one thing. So let us say I have a linear prediction problem, a regression problem. Okay, and we have seen in the previous class, regression problem is a convex learning problem, but it does not belong to any of these. Okay, so let us say for linear regression problem, how will you, so W transpose X minus Y, this is our loss, and let us say squared loss. So this is our linear regression problem. Okay, and we have seen in the last class that it's not learnable. Okay, so just before this, what we did is we defined a few things that made it learnable, right? So apart from looking at the surrogacy thing. Okay, so that's like two storyline going here. So the so here for this linear regression with the squared loss, just before this we did an example, and we said that additionally what did we assume is that these x are bounded, row bounded, right? So we took norm x less than equal to rho, right? And a consequence of this was that this became, the loss function as a function of W became row ellipsis. Okay, or if you want, the one that we proved was, let us say, the mod 1. Okay, and the one that I left was the square one for you, that was beta smooth and so on, right? So let us fix to this ellipsis case. So this is one we proved today, and we said that additionally if I bound the samples, okay, so these x are samples, right? And there are ways usually we do sampling, right? So we do some kind of normalizations when we look at the samples, right? So it may not be very unrealistic assumption, okay, because I have the samples, I can divide by the some normalize it in a way that it remains very nicely within a row. I mean, look, in general, in a realistic sense, x will be bounded because when you work in practice, x are some vectors, right? So obviously x is bounded, right? In general, in practice, when I'm working with the x samples that I get are actually bounded. But you can make them even better by maybe normalizing these x. Okay, so I have these samples x1, x2, and this usually helps. Okay, so in machine learning, you will see that the first step that people do is that they do some kind of normalization of this. Okay, I mean, there are many ways, again, like mean normalization or something, subtract by the mean or so on, and then divide by some number. But all this is related to the fact that if I do normalize, then I get a nicer row. Okay, so that would be, so normalization is a good thing. So what we saw here is that in this example is that if my samples are bounded by rho, then it leads to the loss function being, which is this, loss function being CLB. Okay, we proved this today, right? And hence it becomes learnable for sure. Okay, and in this, so that's one way. Okay, and then we want to see, are there ways to build a surrogate loss functions, a simple one, for let us say regression with a squared loss, let's say. Okay, so are there ways we can do this? Let us say starting with the regression problem with a squared loss. Okay, so that's the part that is discussed in chapter 13, which is about regularization and stability. Okay, so I will do some part of this chapter. Obviously, I cannot complete this today. So let us see, are there any kind of generic ways to make some problems kind of convex. Okay, so convex or stable, they are kind of related. So let me kind of define. So now we are to chapter 13. So far we have missed, I think, 2 chapters, I think 6 or 7. Then we have followed quite a bit. We have missed the chapter boosting, that we will cover later on. So basically we will cover this whole book thoroughly so that you have a very, very good understanding of not just algorithm, but what is the detail behind that. Okay, more rigorous way. So as an initial step, it's always, I always say students, as an initial thing, always go for a little bit of rigor in the beginning. Okay, so that your foundation is good. And so this chapter is regularization and stability. So what we will do in this chapter, the main thing in this chapter is that we will bring in a concept of something called regularization. Okay, so regularization, by regularization we mean that we will make the problem basically more tractable in some sense, because, or in fact it will lead to some kind of convexity. Okay, which is nicer. Okay, or it will move the problem from the domain of non-singularity to singularity, where you guarantee some solution and uniqueness and so on. Okay, so all these are related. So as we go ahead, you will see what exactly it means. But the fact that we will regularize our problem, this will change our problem to a new class of problem. It's called regularized loss minimization. Okay, so what we will actually study is something called, so this changes our problem. Okay, so basically our original loss is there, but we regularize the loss changes. Now it becomes a regularized loss, and hence the problem we study will be regularized loss minimization. So this is a learning framework where we jointly minimize the loss, the empirical risk or the loss risk, and a regularization function. Okay, we will make a we will see what are these regularization functions. In fact, you will see that the role of regularization becomes very, very important. Okay, in machine learning, it becomes extremely important, I would say. Okay, in fact, you pick up many paper, and then at some stage they will say regularize. Okay, so this is an important concept. Okay, because if you don't regularize, you don't know, your problem can be singular. That's the problem. Okay, so it's like solving Ax equals to b, and A is singular. So you are in an uncharted territory. You don't know which solution you will get, right? Infinitely many would be there, and so on. So this also corresponds to that. We will see this in the sense of linear regression, and you will see what I mean. But overall, regularized problems are like this. You have your original loss, but then you have and you add that loss with some regularization function. Okay, so in this sense, let us define a regularization function like this. R from Rd to R, and in this case we minimize argmin W and LSW plus RW. Okay, so as you can see, LSW is your primary loss, okay, that you have as a modeling assumptions, but then you add some RW. Okay, this is a regularizer. Now, why we need this? So we will see this. So one of the simple regularization function would be just RW is just norm of W squared. Okay, that's one way to regularize. Let us see a consequence of such regularization. Okay, so let us consider a simple regularizer. Which in this case is R W is lambda norm W square, where lambda greater than 0 is a scalar, and we are looking for these L2 norm. So this, when I don't write the 2, then it means it's a L2 norm. Okay, so this is a very simple regularizer, lambda times norm W square, where lambda is a constant. We will see the role of lambda depending on how much focus you want to give on the regularizer. Your lambda can be very high or it could be low. Okay, it depends. So if you see the generative modeling course that we have done, while computing the Wasserstein distance, then in one of the papers, Couturier, his main idea was that you do entropy regularization of the Wasserstein loss, and that is a regularization. Okay, he added some Wasserstein loss was there, and then he added some h, okay, lambda times something like that. Okay, so this was the entropy term. So as what I'm trying to say is regularization is a very important concept. Okay, real world problems are very difficult. Okay, and you have to make them tractable. Then you have to do some kind of regularization. So with this regularization, he could make a Wasserstein loss. Computing the Wasserstein distance was very difficult, right? That's why we went by other ways. But this was a very critical paper which just did this regularization, and then developed an algorithm saying that there is a tractable algorithm which can learn this, regularized loss. And what was the intuition that what was the immediate consequence of this? Was that it was making this strongly convex. Okay, so these are the key ideas that that people employ, right? In fact, overall, what you have to understand is that you always want to use convexity. That's the broad statement that I want to make. Okay, because non-convex problems are very difficult to work with. As I said, you will get lost in local minima. There is no guarantee of, and even the methods that you will choose, you are not sure about that. Okay, so going via surrogate and regularization, these are the ways to make a problem go into the convex domain, and then you know algorithms and the guarantee that you have. So here this is a very simple regularization, and we will see an effect of this in, let us say, a regression problem. So what we will define next is the regression problem, but with this regularizer, and then it is called a ridge regression problem. Okay. So even now you will see many papers people publish, they will just keep improving some results on ridge regression and so on. Okay. So so basically this is a well known problem. Okay. So ridge regression. So the way I will just write down this arc mean W, and then you have lambda W squared. So we have added the regularizer, and 1 by m half of W xi minus yi. Okay. So this was our original linear regression loss. So original linear regression loss, and this is the regularizer we have added. So we have added we have added a regularizer. So in your linear regression problem, if you add a regularizer like this, then the name becomes ridge regression. Okay. The ridge is for the fact that this is regularized. Now you could have added one num also, okay, instead of two num. So then it becomes some then it will become some other thing. Okay. So basically there are many ways you can add this regularizer. We are considering only one type of regularizer, obviously, but as you change this, there are different names also. Okay. So let us focus on this for the moment. And now instead of minimizing the original linear regression, now we are minimizing this regularized one. So a minimizer of this, we believe we will take the gradient and equate to 0, right? And earlier we have seen if we take the gradient and equate to 0, then it becomes Ax equals to b form. Now if I take a derivative of this, then it will be lambda I w. Okay. So basically it will be a plus lambda I whole thing multiplied with w equals to the b terms, that this yi and all this will go on the right hand side, and that will give us a b. Okay. So at least for this we have already discussed this in great length in linear predictor chapter, that if I take a derivative of this, then this is like Ax equals to b, where the rows of the A are these xi terms and so on, and then columns of these are the w. Okay. So basically xi transpose xi xj terms are the rows of w. Okay. So so we will not do that derivation again. We recall that this is some Ax Ax minus b type. Okay. So and then we have this as so this is clear that the derivative of this is lambda w basically. Okay. So with this we will now now write down the equations we are supposed to solve with this. Okay. So we take the gradient, equate to 0, and from there we are supposed to solve for w. So in this case, so we take gradient and equate to 0. So if we do that, then we will get 2 lambda m I plus a w equals to b. Okay, where a is xi transpose. Okay, so this is sum of xi transpose equal 1 to m, and then so if you don't recall this, you can like see those derivations that we did a long time ago. Okay, so A will be of this form. Okay, because I also multiply from the x transpose. Okay, so all this we have done this. So A is this, B is that, and that's the linear system we are supposed to solve. Okay, so this you could have written this as x transpose. Okay, so from here what I know is that A is symmetric and positive definite, but not necessarily strictly positive definite, meaning A could be singular. Okay, and the last time when we were doing linear predictor, we said that if it's for unique solution, we want A to be strictly positive definite, meaning no eigenvalues are zeros, and hence it's non-singular, and we can invert this matrix and so on. Okay, and if it is not invertible, then if you recall, we defined a pseudo inverse. Okay, and when we defined a pseudo inverse, but at the end of the day, pseudo inverse is a pseudo inverse, right? So it will give you some solution. So like if this has infinitely many solutions, then pseudo inverse is giving you one of the solutions there. Okay, so at the end of the day, what I'm trying to say is, if it is singular, then it's a bad problem to solve. Okay, and you can create a hack and use pseudo inverse and so on, but at the end of the day, it's a singular system, and AW equal to B is a singular system. So but then the effect of regularizer, now you see, right? If you have lambda m I coming here, right? Now if you add a matrix by a lambda m, let us say some constant, then it shifts the eigenvalue of A, right, by 2 lambda m in this case. So this guy is greater than or equal to 0, but the fact that I added some positive quantity to the eigenvalues, so it definitely becomes non-singular now. Okay, so the effect of regularizer in this case is that it's making your problem well posed. Okay, meaning it's an invertible problem. A is a square matrix for sure, because it's of the form XX transpose, so that's not a problem. The only problem was, and it is also a semi-positive definite, so eigenvalue can be 0 or greater. The effect of regularizer is that it makes it surely greater than 0, hence non-singular, and then this makes the problem well posed. Okay, so that's the role of a regularizer. Okay, it gives you it makes your system stable basically. Okay, so if you don't have this term, then solutions can be infinitely many, and so that's another way to do to stabilize a system, make it well posed, and so on. Now of course you have an handle with the lambda, right? So if your lambda is very large, obviously you are going far away from the given problem. So in this case you have to kind of see, okay, how big of a lambda you want to have. Okay, so ideally if you want to remain close to your problem but still make it non-singular, then keep it small. Okay, just to make it numerically non-singular, so make it as big such that you can numerically solve it, because numerically, by numerically I mean double precision would be roughly, okay, not precisely but roughly like 10 to the minus 16, and usually double precision is used, right? And if it goes below 10 to the minus 16, then it will be treated as 0, and whole thing will be treated as 0 from computational point of view, and you are essentially working with singular systems, and it may lead to some issues. So so lambda is a parameter that you have in hand. It's a hyperparameter. Okay, which lambda is the best? It depends. Okay, it depends on the problem at hand. So you may have to tune these parameters. So this is the idea of And the way we add this regularization like this, okay, specifically like this, this goes by the name of Tikhonov regularization. Okay, so this is the name of some person. Okay, Tikhonov regularization. Okay, so sometimes in paper they might say Tikhonov regularization and so on, but that's what they means. They will add lambda norm w square. Okay, so this is very popular regularizer. Initially, usually people add this, and not just for this kind of loss. This is a linear regressor loss, right? You add this even with neural networks. Sometimes people will add like this. Okay, they will add some lambda norm w square or lambda 1 norm of w. So this is used a lot. Okay, not just with the regression loss. So so in this case, since this is invertible, right? So we can fill this here, right? So here A is positive definite. Or I mean semi-positive definite, right? That's the main part. Is semi-positive definite. Hence, can have 0 eigenvalues. Due to regularization to lambda mi plus a, okay, becomes strictly positive definite. That is non-singular. Okay, it is symmetric, it is positive definite. Okay, if it's non-symmetric, then it's a little bit tricky to define positive definiteness, because positive definiteness also reflects eigenvalues being greater than 0, but then if it's non-symmetric, eigenvalues can be complex as well. So there is a equivalent definition where we say that if a matrix A is positive definite, if the real part of the eigenvalue is greater than 0. Okay, but that is usually not very common to say that. Okay, so we say positive definiteness usually with symmetric matrices. Okay, so this is non-singular, so I can take an inverse here. Okay, so we can take inverse, usual inverse, and we will have a unique solution there. Okay, so we have like some minutes. Okay, 10 minutes maybe. Okay, let's see. So there is a theorem that I'm supposed to. So basically, the stable rules don't overfit. That's one of the things, but maybe we have to postpone this later. So the idea here is that there is a concept of stability, meaning that I train on certain number of m samples, but I can remove one of them and replace by some other. Okay, just one of them, and still the error is not very high. So that is called stability. Okay, and Tikhonov regularization brings stability. Okay, so these are the sequence of things we want to do. Okay, we will understand stability, and then next step is like doing this brings the stability, and stable rules are also learnable. Okay, so stability leads to learnability. Okay, so that's one of the results, but we won't be able to do those things today. So what I will do is that I will try to wrap up in like 10 minutes. So to conclude that, so we can solve, hence W can be given as 2 lambda m I plus A inverse B. So we can solve W like this. So in next section we will, so maybe not today, just to keep it as a highlight. So in the next session we will show that regularization stabilizes the algorithm. I have not defined the stability. I have just orally told you that if I just change one training data, still the error is not very high. Okay, so that's usually the stability, but we will kind of make it concrete. Okay, so the regularization stabilizes the algorithm and prevents overfitting. What happens usually is when we do the regularization, then one of the intuitions that you have is n plus some loss in W, okay, and you are supposed to minimize. So the way it might prevent overfitting is because of this term. So what we are trying to say is that regularization prevents overfitting, and the way to understand this is that the fact that you have this term. Now if your weights are high, or let us say many of the weights are allowed, okay, then it's essentially the hypothesis class that you are taking has a lot of freedom basically, okay, and if it has a lot of freedom, it might fit the training data very well, okay. But if I put this here, then if I minimize, then with a larger choice of lambda, what I am telling is that although you are minimizing the loss, okay, you are trying to fit a curve or whatever to the data, but I won't allow you to I don't want the W's that you are choosing to be high, but then actually it's more than that. So let us try to understand this in an intuitive way, okay. So as I keep saying, my favorite, this curve fitting problem, right? And let us say the W are the coefficients of the polynomial. So let us say PW is our W0 plus W1x plus W2x square plus W3 x3 plus dot dot dot, okay, plus Wn xn. So my weight vectors of my model are this vector W0, W1, W2, Wn that I am trying to learn, okay. So basically we have seen this also in the linear regression part, that even with the polynomial it's a linear regression because I can see the vector W applying on the transform features like 1x, x square and so on. Okay, so if you can recall these things that we did previously. So sticking to this, so let us say you don't have this, right, and you picked a W which is let us say the polynomial because you didn't know in advance, because usually this is your this is the inductive bias that you have to pick, right, because this is something which parameter model I will use is chosen in advance. That's an intuition you will use usually. And let us say you pick this polynomial to fit, where n you don't know in advance. Now maybe this n is too big for the network. I mean too big in the sense that it will employ a very high degree polynomial like this, okay. So in this case what happened is that without this term I gave a complete freedom, even though my choice of n is some finite, I give a complete freedom to choose a model which is perfect on the training data. This is perfect, like it did not miss anything because it has like the degree was good enough. But now let us bring this term now, okay, and lambda is a quantity that is in my hand, right. So if I say lambda is very high, okay, so lambda is maybe, it depends on the context, right? So it should be higher compared to this, right? So if it's, I mean, if this guy has to play a role, then these two are related, right? So the optimizer is trying to minimize both, but it will see like where it gains the most, right? Eventually it tries to minimize all, but this guy will have a role now. Now if the lambda is very high, then for the optimizer it makes sense to keep some of the weights 0 also, okay, because the norm of the because negative also is going to contribute because it's norm squared. So the best possibility to minimize W is to keep some of the W's 0 also, okay. So then the optimizer is like looking into this. So in that case what it will prefer would be to make W for which some components are 0, okay, like not 1, like some number, right? So let us say W3, W1, it gives some values, then 0 0, and then W4, and then N0 maybe, okay, because it has the incentive now, because if it keeps others non-zero as well, then the overall cost will be very high for the optimizer. So the effect of the regularizer like this is that it implicitly forces to use a model which is smaller in size. So a smaller size model would basically would mean that it will choose a model which will make an error, because now there is an incentive to also pick this smaller, right? So then it will pick a smaller size model basically. So a smaller size model may not do so much of a best fitting we expect. So it might make some error, but it will go like this, okay. So because it did not have the freedom to choose all the W's, but now because of the fact that I'm making this reasonably high, it will make some component 0 for sure, and but then if it does that, it is expected that it is doing a trade-off that it will make some error, training error on the given sample, okay. So what will happen then, because of this guy, it has forced the model to not overfit, because this guy is clearly overfit, okay, because if I have a training data here, okay, and then the data was somewhere here, because as I said, machine learning problem, the data itself may not be perfect, okay. So there sometimes during data collection you may have some error, some error like that, okay. So fitting everything perfectly is not a good idea, okay, in general, okay. So and usually in the very first or second class we have said overfitting is a memorization. Memorization is not learning, okay. From machine learning point of view, if you memorize, then you will not generalize, okay. So that holds true for mathematics, right? If you memorize everything in maths, then perhaps you will not be a good researcher maybe, okay. So you have to think about the generic pattern, right? So here it memorized, so then it was supposed to be here, so it will make an error. But then with this guy, right, with the regularizer, it is making lesser error compared to the guy that was perfect. And so we have discussed this couple of times. So coming back to the role of the regularizer is, it will make this effect. It will help you choose a model which is more modest, lesser in complexity. So when we say lesser complexity, means that the whole model reduces to just like a couple of weights, okay, others were not used. So lesser complexity model, which may likely not overfit, okay. So that's why we say that it prevents overfitting, okay. This is how we are intuitively explaining that it prevents overfitting. Okay, I think we can stop for today, because the theorem 13.1 is not proved, it's just stated. So we can state it next class also, and then we prove that. So for the moment, let us stop, and we will prove stable rules don't overfit and so on.